Imagine the universe in its first moments, a time less than a second after the Big Bang. It was a searing, chaotic soup of energy and fundamental particles. Everything was hotter and denser than anything we can imagine. The laws of physics themselves were still settling into place. As this primordial universe expanded and cooled with incredible speed, it went through different phases. Think of it like water freezing into ice. This rapid cooling wasn't perfect. Sometimes defects were left behind. These aren't just any flaws, they are cosmic strings, titanic threads of pure, concentrated energy, thinner than an atom's nucleus but stretching across unimaginable cosmic distances. To understand how these cosmic strings might have formed, let's use a simple analogy. Picture a frozen lake on a cold winter day. As the water cools and turns to ice, it doesn't freeze all at once in a perfect, uniform sheet. No, it starts to crystallize, in different places, with the ice crystals growing and meeting each other. The boundaries where these separate patches of ice meet aren't always perfect. They can form long, jagged cracks. Cosmic strings are like those cracks in the ice, but on a universal scale. They are the boundaries left behind when different regions of the early universe froze into their new state at slightly different times, trapping raw, high-energy leftovers from the Big Bang itself. These are not your ordinary strings. They are one-dimensional defects in space-time itself. They are relics from a time when the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were all one. As the universe cooled, these forces split apart, and in the process these energetic scars could have been etched into the very fabric of reality. They would be incredibly dense, with a small section just a mile long weighing more than our entire planet. These strings would be under immense tension, whipping through the cosmos at nearly the speed of light, oscillating and vibrating like the most powerful guitar string in the universe. So, what are we left with? We have these hypothetical, ancient relics zipping through the cosmos. They are invisible threads of immense power, born from the most extreme conditions the universe has ever known. They are not made of matter, as we know it. No protons, no neutrons, no electrons. They are pure, raw energy, a fossil from the moment of creation itself. Their existence is predicted by some of our most advanced theories about the universe's origins. Finding one would be like finding a preserved footprint from the first second of time, a direct link to the Big Bang that we could see and measure today. What would happen if you encountered one of these cosmic behemoths? Well, you wouldn't see it directly, but you would feel its presence. A cosmic string possesses an immense gravitational pull, not because it's a big, round object like a star or a planet, but because of its sheer density and tension. Einstein taught us that mass and energy warp the fabric of space-time, and that's what we call gravity. A cosmic string, with its incredible concentration of energy, would warp space-time in a very peculiar way. It wouldn't pull you in from all sides like a planet. Instead, space-time around a cosmic string is shaped like a cone. It's flat everywhere, except at the string itself. Imagine a flat sheet of paper. That's your space-time. Now, cut a thin wedge out of that paper and tape the edges back together. You've just made a cone. The paper is still flat everywhere you can draw on it, but the overall shape has changed. That's what a cosmic string does to the universe. This unique gravitational signature has profound effects. Any object, even a whole galaxy, that passes by a cosmic string would get a gravitational jolt. The string could act as a seed for matter to clump together, potentially explaining how the first galaxies and the large-scale structures of the universe formed so quickly after the Big Bang. This cone-like geometry does something truly strange to light. If a cosmic string were to pass between us and a distant galaxy, the light from that galaxy would have to travel around the string to reach us. From our perspective here on Earth, it would look as though the light came from two different places. We would see two identical images of the same galaxy, side by side in the sky. This is a special kind of gravitational lensing. Finding a pair of galaxies that are perfect mirror images, with no massive object between them to explain the lensing, would be a smoking gun. Powerful evidence that a cosmic string is lurking there, invisibly bending the light. The effects don't stop there. A moving cosmic string could slice through a galaxy, triggering a wave of star formation as it compresses gas and dust. Or, if two strings were to cross, they could reconnect in a new configuration, snapping off a loop of string. These loops would then oscillate wildly, radiating away their energy in the form of gravitational waves. ripples in the fabric of space-time itself. These loops would eventually decay and disappear, but while they existed, they would be among the most powerful gravitational wave sources in the entire universe, shaking the cosmos with their violent death throes. So, how do we find something that's thinner than an atom, possibly billions of light years away, and completely invisible? We can't use a telescope to just look for one. We have to be clever. We have to search for the clues they leave behind, their fingerprints on the cosmos. One of the most promising methods is to listen, not with our ears, but with instruments designed to detect gravitational waves. As we discussed, oscillating loops of cosmic strings would be powerful sources of these waves. They would create a constant, faint background hum of gravitational waves rippling across the entire universe, a cosmic symphony playing since the dawn of time. Our gravitational wave observatories, like LIGO and the future LISA space antenna, are our ears to the cosmos. They are designed to detect the tiniest vibrations in space-time. By analyzing the data from these observatories, scientists are searching for a very specific type of signal, a continuous, stochastic background noise that is distinct from the chirps of colliding black holes or neutron stars. Finding this persistent hum would be like hearing the echo of those ancient strings vibrating across cosmic history. It would be a monumental discovery, confirming not only the existence of cosmic strings, but also giving us a new window into the physics of the early universe. Another key search method involves looking for their unique gravitational lensing effects. Astronomers use powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope to survey the sky with incredible precision. They are on the lookout for those telltale pairs of identical galaxies, or quasars. It's a cosmic game of spot the difference, or in this case, spot the identical twins. Computers sift through mountains of data, comparing images of countless celestial objects, searching for a perfect match that can only be explained by the conical spacetime of a cosmic string. It's a needle in a haystack search, but the payoff would be enormous. We can also look for their imprint on the oldest light in the universe, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. If a cosmic string was present back then, its gravity would have left a subtle mark on this ancient light. It might appear as a sharp line-like discontinuity in the temperature of the CMB, like a faint scratch on a photograph. Scientists at the Planck satellite mission and other experiments meticulously scan maps of the CMB, looking for these specific patterns that would betray the presence of a cosmic string in the early universe. The search for cosmic strings is about more than just finding an exotic object. It's about testing the very limits of our understanding. If we find them, it would revolutionize cosmology and particle physics. But what if these strings could do even more? Some of the more speculative and exciting ideas in theoretical physics paint an even wilder picture. For instance, the immense energy in magnetic fields around a cosmic string could act as a natural particle accelerator, flinging particles to energies far beyond anything we could ever hope to achieve on Earth. They could be the source of the mysterious, ultra-high energy cosmic rays that occasionally slam into our atmosphere. Let's push the boat out even further. Some theories suggest that certain types of cosmic strings, or the collision of strings, could create even more exotic phenomena. Could they open up gateways through spacetime? Perhaps a cosmic string loop, under the right conditions, could stabilize a wormhole, a theoretical tunnel connecting distant parts of the universe, or even linking to other universes entirely. While this remains deep in the realm of science fiction for now, it highlights just how profoundly these objects could change our perception of reality. They represent a bridge between the theoretical and the observable, a place where our wildest ideas might just be true. The importance of this search cannot be overstated. Finding a cosmic string would be the first direct evidence of the physics of the Grand Unification era, the time when the fundamental forces were one. It would validate an entire class of theories about the universe's birth and provide concrete data about an epoch we can currently only dream of. It would be a discovery on par with the detection of gravitational waves or the discovery of the Higgs boson. We would no longer just be modeling the Big Bang. We would be observing one of its most incredible creations directly. Ultimately, the quest for cosmic strings is a quest for our own origins. It's about understanding how the featureless, uniform soup of the early universe evolved into the magnificent, structured cosmos we see today, filled with galaxies, stars, and us. These cosmic threads, if they exist, are a fundamental part of that story. They are a reminder that the universe may still hold secrets from its very first moments, secrets that are woven into the fabric of space-time itself, just waiting for us to find them. The search continues, because the potential prize is nothing less than the story of everything.